So chapter 3 is those exponential and logarithmic functions that we've kind of seen a little bit about. So today for section 3.1, it's exponential functions. So we're just going to kind of go through writing out like a definition of an exponential function, do some examples of them, do a little graph, and then talk about translation. So translations is being able to move the function or move the graph, and works no different than if it was a quadratic or any other function. So just a quick little overview on how that looks when it comes to exponential functions. And then tomorrow we'll get into a little bit more of looking at compound and continuous interest, which has to do with exponential functions. So let's start off with what is an exponential function. So we know it's a function, so I'm just going to go with f of x because it seems like that's what we always go with. And we write it as b to the x. And we say that b equals our base. Right? So in order for it to be an exponential function, where's our variable? Oh, there's our variable. So our variable is an exponent. So since our variable is in the exponent, we call them exponential functions, right? And again, if we didn't want to write it as f of x, another letter for f of x, we could say that it was y equals b to the x, right? So either which way. So let's go with some, if we can figure out if they're examples or not examples of exponential functions. So if I had, let's say, f of x equals 2 to the x. So my base is 2. And where's my exponent? My exponent, or my variable is in the exponent. So that's an example of a exponential function. So this one would be exponential. What if I had f of x equals x squared? Would that be an exponential function? No, this one's actually a quadratic, right? So I always look for where's my variable. Well, my variable on this one is technically the base, and my exponent is 2, and when my exponent is 2, I know it's a quadratic, right? What if I had f of x equals 3 to the x plus 1? What do we think this one is? Yeah, exactly. Oop. This one is exponential. Right? What's my base? My base is the 3. And then in my exponent, I have my variable. So since my exponent's in the variable, it's going to be exponential. Oh, I got a good one. What if we had, let's say, f of x equals x to the x? Is that one going to be exponential? No, this one's not exponential. Because your variable of your base is constantly changing, because that's your variable as well. So this would be like 2, like if you put in 2 for x, it would be 2 squared, or it would be 3 to the 3rd, 4 to the 4th, 5th to the 5th. So you're never growing just in your exponent, your bases as well. So it's not exponential. And another kind of cheesy one is, let's say we had 1 raised to the x. And this one's the tricky one, right? Because if we go by our little definition of our base and our exponent, our base is 1 and our exponent is that variable x. But if I take 1 and I raise it to anything, what do you think I'm going to get? 1 squared is 1. 1 to the 5th is 1 times 1 times 1 times 1 times 1, which is going to give me 1, right? 1 to the 0 is still going to give me 1, right? So regardless of, when it comes to this 1, regardless of whatever our exponent is going to be, it's always going to equal 1, right? There's no way of getting around it. So on these, this is going to be not exponential either. So if we need to evaluate, so if they gave us 2 to the 3.4, we're just going to put that into our calculator, right? And everybody knows where our little caret button is, so we're just going to put in there 2 to the 3.4, and then you're going to get an approximation of like 10.56. Go to the nearest hundredth, right? Another example they might give you would be where the base is 5 and they want you to raise it to like the square root of 3. Right? So really this is just a matter of making sure you know where all of your little fancy buttons are on your calculator, and we can get it up to our exponent. So if I did 5 times the, and I don't know this one, I gotta put it in my calculator, 5 times the square root of 3, I'm gonna get another approximation because it's a non-ending, non-repeating decimal of like 16.24. And then there's another very special one that we're going to talk about, and it's the letter E. So like, let's say I want to do e to the negative 1.2. So we want to be able to find e on our calculator. And I don't have a calculator on there. Anywho, if you have a graphing calculator, if you use like decimals, it'll give you where the e is, but it would be in that first column. We'll go on a graphing. It's in the first column. And 1, 2, 3, 4, 5, 6, 7. Mine is 7 down, and it's actually the natural log button, but you have to do the second. So mine is the second, and then that ln, and that'll get me to e. And when I put it in my calculator will literally show e, and it's already raised to the exponent. If I do negative 1.2 and I put it in, I'm going to get 0.31, right? So if anything, this is a good little spot to write these down. So when you go to check it into your calculator, just to make sure you're putting it in correctly, try putting it into your calculator and see if you come up with those same answers. If you don't come up with those same answers, get a hold of me and we'll figure out where the glitch is. Sound good? All right. So we want to be able to graph these exponential functions, right? And we want to be able to, just like in the last chapter, we want to get away from relying on that technology of doing all of the work for us. We want to understand how functions work and how to move things around and how they actually kind of graph. So it does say in there like to try and graph it by hand, and then of course put it into the calculator or into decimals to double check to see if you're doing it right. But we want to be able to get into being able to figure out our numbers correctly, being able to do that arithmetic correctly, and then being able to plot those points and having a general understanding of if it's supposed to look the way that it does. So let's go ahead and graph. Let's go with f of x equals 2 to the x, right? So our goal a lot of times is being able to write it as an equation. Well, they gave us the equation, so I think we can write it as an equation. And then it's to make a table, and then to make an accurate table, and then to be able to graph those points that are on the table, right? So let's go with a table. So we'll have our x values, and then we want to put those into f of x, which is 2 to the x, and then that'll give us our y value. And you don't have to make your table exactly like this. You can make your table however you want. Some people even like to do it horizontally and write it across that way, and that's fine as well. And then I'm just going to go ahead and make my XY coordinate plane, because honestly I like to find the point, plot the point, find the point, plot the point, but you can do it however you wish. So let's go with 1, 2, 3, 4, 5. 1, 2, 3, 4, 5-ish. Okay. 1, 2, 3, 4, 5. Oops, no. I think that'll get us started at least. Right. Alrighty. So when we graph these, we want to do some negatives and some positives, right? So I'm just gonna go with a start with a -3. I like negative exponents. See if we can remember how to do these. So this would be 2 to the -3. And when we have bases raised to negative exponents, because we're not supposed to have negative exponents, we have to flip those, right? So to get rid of that -3, that's going to equal 1 over 2 to the 3rd, which is going to give us 2 times 2 times 2 is, 8. So that's going to give us 1 over 8, right? So I'm going to go ahead and plot that point. So at -3, I'm at a positive 1/8. So I'm just going to give myself a dot right about there. Right. So then let's try -2. 2 to the -2. My exponent is negative, so I gotta do the reciprocal. So that's 1 over 2 squared, and 1 over 2 squared is going to give me 1/4. So at -2, I'm at a 1/4, so I'm up a little bit, right? What happens when I put in -1? 2 to the -1. Negative exponent, I got to do the reciprocal, so 1 over 2. If you want to put a little 1 there, you can. And that's going to give me a half. So at -1, I'm at a half. Hey, I'm growing, I'm getting there. I can put in 0. 2 to the 0. We know that any number raised to the 0 is going to give us 1. Good job. Hopefully we remember that from our mathematical experiences. So I'm going to plot that point. Then I'm going to throw in 1. So 2 to the 1. 2 to the 1 is 2. Right? So at 1 we're at 2. Oh. If I put in 2, 2 squared is 4. So at 2, I'm at 1, 2, 3, 4, right? And then if I wanted to, I could put in 3. 2 to the 3rd is going to give me 8. Right? So at 3, I'm at 8, so I'm going to be way up here. Yeah. So hopefully we can see that that's going to give us our exponential growth, right? And then we know that our functions are continuous. So we're just going to try and draw a nice little smooth, continuous line or graph going that way. And then this one's going to get really close to that 0 axis, but it's not going to go below it, right? So we know that, or the x-axis, so we know that x-axis is probably a asymptote, right? And then I know we love domain and range. So we can talk about our domain. Domain are our x values, right? So we have to think of what x values can we use. Well, I can use all of these guys, and I bet you I can keep going this way, right? There's no restrictions on my x. And the same thing, I'm going to keep going this way. Granted, it's going to skyrocket up the y-axis, but I can keep putting in numbers. I can put in 2 to the 1,000 or anything along that lines, right? So when it comes to our domain, we know that we can use all of our x values this way and all of our x values this way. So we're going to go from -infinity to positive infinity. Right? And if we do our domain, we might as well do our range, which are our y values. So when it comes to our y values, what's the lowest y value we came up with? Well, we realize it's getting really, really, really close to 0, but it's not going to be 0. And then as I go up, I'm using all these different y values. So I know that I can get close to 0, but I can never set that baby equal to 0 and get it equal to 0. So I'm going to have a parentheses for 0, and then I'm going to keep going all the way through positive infinity. Sound good? All right. Just real quick, instead of doing another graphing one, I just want to make sure that we understand a little mathematics. So if I give you guys the function like g of x equals 1/2 raised to the x, and then you guys are going to make like your table, right? And then 1/2 to the x, and then that's going to give you your y value, right? When I put in, I don't know, let's pick this, let's say we picked in 3, just to keep the numbers a little bit separate. We know that this is 1/2 to the 3rd, right? But by the power property, it doesn't necessarily matter on this one because I have a 1 on the numerator, but that 3, who does that 3 get shared with? Just the top, just the bottom, or with both the top and the bottom? Yeah, it gets shared with the top and the bottom, right? So this is the same thing as 1 to the 3rd over 2 to the 3rd, right? So I just want to make sure you guys remember that. If you have a fraction raised to an exponent, that baby gets shared with everybody inside, right? Alrighty. So let's go over translations. So translations is just how you were moving graphs. Right? Are we moving it up? Are we moving it down? Are we flipping it? Are we doing all that good stuff? So I'm going to stick with that function that we just worked on, that f of x equals 2 to the x, right? And then if we made our little graph again, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? Then you can refer back if you need to, right? Look for, we crossed the y-axis at 1, right? And then kind of went up pretty straight, pretty consistently, right? 1, 2, and 2, 4, right? So I know we crossed at 1, 2, and 2, 4. And not that this has got to be perfect, but, right, and we're getting close. So that's your parent function. Right, we refer to a lot of those times as the parent function. Parent function is like the one that you're starting with before you do any translations to it or do any moves to it. So let's say we wanted to look at, I'm going to go with g of x, and I'm going to go with 2 to the x, but then I'm going to add 1 to it, and the 1 is not with the x, it's not up in the exponent, it's on the same plane as where the 2 is. So if we go back to when we were learning about like translations when it came to quadratics and all that good stuff, there was a difference between if whatever we were adding or subtracting was with the x or if it was without the x. And this one is without the x. So this would be, you know, if you thought of like, oops, there you go. So this isn't with the x. So this one is going to move our function up or down, right? So I'm going to take my whole graph that I just had, and because it's plus 1, I'm going to move it up 1. So instead of crossing the x-axis at, or sorry, crossing the y-axis at 1, I'm now crossing it at 2, right? And then when it comes to how on my orange graph, remember my x-axis became my asymptote? Well, I'm moving everything up 1, so what's my new asymptote going to be? My new asymptote is going to be that 1. So we're going to get a graph that looks something along the lines of this, right? And then we could talk about, well, what if we did 2 to the x plus 1? So then, the part that's changing, is it part of the x? Yeah, it's part of the x. So since we know that x has to do with horizontal shifts, then this is going to give us a horizontal shift. And this is actually going to give us a horizontal shift to the left one, right? So we're going to take like our little orange graph, but we're going to take that whole thing and we're just going to shift it over one. So I'm still going to cross again at 2, right? Because I was crossing, oops, let me go my little pointer. I was here, but I got to move it to the left one. So where's this guy going to go? He's going to go here, right? This guy, where's he going to go? He's going to go here, right? So this one would be like right about here. So we're still going to come down. It's going to get sloppy, isn't it? We need some more colors now. Oh, I bet you I could do yellow on here. Oh, well, I think we'll be all right. All right. What if I had I of x equals negative 2 to the x? Well, what happens when we put negatives out front? It flips it over the x-axis, right? So instead of now crossing it at a positive 1, I'm now going to cross at a negative 1. And then when it comes to my asymptote, I'm still going to have my x-axis as my asymptote, but instead of getting really close to it from up here, I'm going to get really close to it down here. And then if you want, right, so whoops, that crossed at -2, so that would have been at -2, that would have been like -4, right? This guy, and like that. Not too shabs. So those ones are 3, if not like 4, if you take the parent graph, right? So if you have your parent graph, if you have your plus or minus and it's not part of the x, that's going to be a horizontal, right? If this was, say, a -3, what would have happened? That whole entire graph would have dropped down 3, right? This one is with the x, so we know it's going to be a horizontal shift, and it's going to be a horizontal shift to the left one. Remember how that formula works? That's actually like an x minus h type thing, right? And if we have a negative out front, it's going to flip it over the x-axis. Sound good? All right. Tomorrow we'll talk more about E and how they came up with E. E is called the, it's a natural base, the natural base of E, right? And E technically is like pi. It's a never-ending little number, and it's what, 2.7188, no, sorry, 8281827, right? And then it keeps going on and on forever. Yeah, so remember like when you used to learn pi, you know, pi is 3.11492. You can do the same thing with natural base. So tomorrow we'll talk about what natural base is, where that number comes from, and how and why it's useful. Sound good?